Before we continue on the core topic, this series of lecture video is meant to beef up your math foundation. We will start with the topic on coordinate system, and I will start with a question to illustrate the needs for coordinate system in physics. Where is the tree? This is a question about position, which is an important quantity in physics. You ask both our boy and our girl. Now, before we proceed further, for our own convenience, we define left and right from our perspective. Left, right. So our boy will say, it is on my right, and our girl will say, it is on my left. Who is right and who is wrong? How can the same tree, a physical object, be at two different locations at the same time? Well, this sounds like a stupid question. Obviously, if you see at the diagram above, both are right, depending on, I would like to emphasize that phrase again, depending on, who do you ask? The tree is on our boy right, and it is also on our girl's left. In physics, we have a better technical term to describe depending on. That term is called relative. The tree is on the right relative to our boy. At the same time, it is also on the left relative to our girl. Having said that, this is still going to pose a problem, isn't it? If the answers to physical quantities are relative to whom you ask the question to, how are we going to come into agreement over more complicated matters later on? The solution to this problem is to come up with a coordinate system that looks something like this. Such coordinate system is what we technically call as Cartesian coordinate, named after the French mathematician and philosopher René Descartes. Okay, so let us look at the feature of this coordinate system. First, there is an axis, which we conveniently call x-axis. The two arrows at the end of the axis indicate that the axis extends to infinity on both directions. Scales are drawn on the axis. In this case, the scales are drawn at unit interval. Also, do not forget about the physical unit in the scale. Remember what we learned from previous lecture? In physics, numbers without unit does not make any physical sense. Second, there is another axis, which we conveniently call y-axis. The most important feature about the y-axis is that it has to be drawn perpendicular to the x-axis. Mind you that it doesn't look perpendicular in this particular image because you assume a third-party bird's-eye perspective. But if you, for a moment, imagine a ground where our boy is standing, the axes are perpendicular when drawn on this ground. And similarly, the y-axis also carries scales. In this case, the scales are drawn also at unit interval, though the scale interval at y-axis can be drawn differently from the x-axis. With the scales are in place, any point on this so-called xy plane can be represented by a pair of coordinate xy. Notice that x must precede y. That is, x must be presented first, followed by y in writing. By this construction, the point where the two axes intersect, which in this case we also choose to be the point where our boy stands, is given by the coordinate 0, 0. This special point is also called the origin of the coordinate system. So back to our question, where is the tree? In our boy coordinate system, when I said our boy coordinate system, I'm referring to a coordinate system where our boy is standing at the origin of the coordinate system. So in our boy's coordinate system, the position of the tree is given by 7, 2. By the way, from now on, I will simply drop mentioning the unit when referring to a coordinate, but it is understood that it should come with a unit for it to make physical sense. 7 in reference to the tree position along the x-axis, which is 7 meters to our boy's right, and 2 in reference to its position along the y-axis, that is 2 meters behind our boy. It is straightforward to extend this two-dimensional Cartesian coordinate system to its three-dimensional version. To do so, we need a third axis which is perpendicular to both x and y axis. Guess what is this third axis called? By convention and convenience, we call this third axis z-axis. Any point in this space can now be pinpointed using a 3 numbers coordinate. For example, the bird sitting on the tree branch is located at point 5.535. 5.5 is in reference to its position along the x-axis, 3 to its position along the y-axis, and 5 to its position along the z-axis. That is 5 meters above the ground. Do pay attention to the sequence. It is always x followed by y and followed by z. Now, is our boy's coordinate system is the only coordinate system we can use to describe the position of the tree and the bird? Well, of course not. In similar fashion, we can also describe the position of the tree and the bird using Argall's coordinate system. That is a coordinate system where Argall is at the origin of the coordinate. In Argall's coordinate system, the tree is located at point -60. Notice how negative is used to describe any position on Argall's right, and the bird is located at -7.515 in reference to 7.5 meter to Argall's left, 1 meter along positive y direction, and 5 meter above the ground. So far so good. Now, this is the interesting thing, so pay attention. You see, after all this discussion about coordinate system, we still come to the same conclusion. That is, our boy and Argall will describe the exact position of any object in space differently. The position of the bird is 5.535 according to our boy, and -7.515 according to Argall. That is hardly surprising because our boy's coordinate system is different from Argall's. Nonetheless, if you are talking about relative distance between any 2 points in space, it is going to be the same for both our boy and Argall. For instance, if we ask them what is the distance of the bird from the ground, both will answer with certainty 5 meter, as illustrated in the diagram. This is not a coincidence. In fact, not just in our boy's or Argall's coordinate system, the distance between any 2 points, such as the distance between the bird and the ground directly under the bird, is the same regardless of any coordinate system used. Now, in physics, most of the time, it is actually not the absolute value of the quantity itself which is important. Rather, it is the difference that matters. For instance, as we are going to learn soon, it is not the position of the bird or individual points that matters. It is the distance or displacement between 2 points that matters. From this displacement, we can compute velocity, and from the difference in velocity, we can compute acceleration. And knowing the acceleration is one step closer to knowing the force. Force is all that matters. Or remember the law of gravitational force we briefly touched in the last lecture series. F equal to G m1 m2 over r squared. The strength of the force is inversely proportional to the distance squared between the two masses. And because the distance between any two masses is the same regardless of coordinate system, the strength of gravitational force between any two masses in space is also the same regardless of coordinate system used. To put it simply, the law of physics is independent of coordinate system. This should be the case, otherwise our boy would live in a world that obeys different set of physical laws from that of our girl, which needless to say doesn't make any sense. The use of Cartesian coordinate to describe a point in space also brings us insight. First, we learn that in two-dimensional space, two independent axes are required and a pair of number x and y are needed to pinpoint any point on the plane. In three-dimensional space where we live in, three independent axes and hence a triplet of numbers x, y, and z are required to pinpoint any point in the space. If you have heard something called string theory, the theory suggests that we are living in a 10-dimensional space. 3 are what we are experiencing on a daily basis. The remaining 7 dimensions are hidden from us. How will you visualize a 10-dimensional space? Well, graphically it is difficult, if not impossible, to visualize such thing like 10-dimensional space. I do not know how to draw a 10-dimensional space on paper, but mathematically it is not that difficult to do so. In the same way, a 3-dimensional Cartesian space requires a set of 3 numbers, a 10-dimensional Cartesian space requires a set of 10 numbers to describe any point in it. Also, Cartesian coordinate system is not the only coordinate system known in physics. Depending on the symmetry of the system we are dealing with, physicists often deploy spherical or cylindrical coordinate system. I'm not going to discuss any non-Cartesian coordinate system in this lecture simply because we are not going to use any other coordinate system other than Cartesian in this course. Nonetheless, I will still encourage you to visit the Wikipedia site.